This section is about forces and motion. It covers pressure, how forces change shapes, distance, speed and acceleration, and forces and motion. First, pressure. Let's remind ourselves what pressure actually is. Pressure is the effect of a force acting on a surface. The pressure on a surface depends on the force and the area of the surface the force is acting on. This clip explains how.
In extreme close-up, you can see the cutting edge of a knife isn't totally sharp. It's a very small surface. A sharp knife has a much smaller cutting surface than a blunt one. When you cut, you apply a pushing force to this surface. The larger the surface, the harder you have to push to cut. It's the pressure of the knife on the apple which makes it cut. This pressure depends on both the pushing force and the area of the cutting edge. If you stand on something squashy like sand, you can easily see the pressure caused by your weight acting over the area of the sole of your shoes. It's the pressure which produces footprints. I weigh the same, but my footprint is deeper wearing this than this. The pressure depends on the area of the sole of the shoe. So, as my weight stays the same, if I double the area of the sole of my shoes, I should halve the pressure. As the area gets bigger, the pressure gets smaller. So, the footprints from my red shoes are deeper than the green ones.
So the two key points are that the greater the force, the greater the pressure, but the greater the area, the smaller the pressure, because the same force is spread over a large area. There's a formula for this. It's pressure equals force divided by area. That's P equals N for newtons divided by m squared, that's square meters. So the unit of pressure is newtons per square meter, or pascals. Can you think of things that work better by spreading a force over a larger area or by concentrating it in a smaller area? Skis and snowshoes reduce the pressure on the snow by spreading your weight over a larger area to stop you sinking. Some animals have large or webbed feet to stop them sinking in mud or sand. And caterpillar tracks stop heavy vehicles sinking into the ground. On the other hand, a drawing pin has a large area to push your thumb on and a much smaller area at the point. That means a much greater pressure is applied at the point than you can apply with your thumb. Hydraulics is something else that makes use of the way pressure changes with area. Liquid can't be compressed easily because the particles in a liquid are so close together. Because of that, pressure on a trapped liquid is transmitted through the liquid. Here's a diagram of a hydraulic car jack. On one side of the hydraulic jack, the car exerts a large force over a large area platform and exerts a certain pressure on the liquid. The liquid is not compressed, so that same pressure, that's force per square metre, is transmitted through the liquid to the piston on the other side of the jack. Here, the same pressure can be held back by a much smaller area of piston. That means it only needs a much smaller force to hold the car. Next, pressure in gases. Watch the next clip and try and work out the relationship between the pressure and the volume of a gas.
These cylinders are a diver's life support system. Inside each one is a phone box full of air, compressed down so much that the cylinders actually get heavier as they're filled. The air inside weighs as much as 3 bags of sugar. Let out all at once, that air would blow a diver's head off. So a mouthpiece releases it slowly, regulating the pressure to keep the diver alive for up to an hour underwater. Divers know that everything depends on their equipment working perfectly, so they check and double-check it on the surface. Down below, it could be too late. It's going up and down that can cause problems. Divers must wait for their bodies to adapt to the change in pressure on their skin and inside their heads. As Charlotte dives deeper, she can feel her body being squeezed. That's pressure. It happens because the weight of the water in a column directly above is pressing on her skin.
You can see that as I descend with this empty plastic bottle, the bottle is crushed as the air is compressed inside.
The air is still inside the bottle. It's just being compressed into a smaller space by the force of water weighing down from above. The plastic buckles because it's not strong enough to withstand that force. This glass jar is open at the bottom. As the pressure increases, it forces water into the jar, reducing the surface area of the air trapped at the top.
In fact, as the pressure on the pocket of air in the cylinder from the water above increases, the volume of the air gets smaller.
The pocket of air shrinks, even though no air escapes.
The opposite is also true. When the pressure on the gas in this fizzy water is released, its volume increases, and out it rushes. We saw that, unlike a liquid, a gas, such as air, can be compressed, and the volume it occupies gets smaller. So if the pressure on a gas increases, its volume decreases, and if the pressure decreases, its volume increases. Another way of saying that is that the pressure and volume in a gas are inversely proportional. There's a formula for this, which says that for any gas, pressure times volume is constant, assuming the temperature stays the same. This is Boyle's law. That's the end of the section on pressure.